The next presentation, the last presentation of the session is from Georgia Tech. It's entitled New Physical Model and Experimental Measurements of Copper Interconnect Resistivity Considering Size Effects and our familiar friend line interruptance. It's going to be presented by Gerald Lopez.
Thank you, Mr. Chairman. So, from the title, you can see that we're going to talk about a model, and it's a closed-form model describing resistivity in terms of both size effects and line interruptance. What we also did as an added benefit was we have in-house capabilities to manufacture our own interconnects. Maybe not as advanced as industry, but it's something certainly similar to where we can calibrate this model too. So to begin, we're aware of this aggressive scaling that we're doing in industry right now. And as we scale interconnects, obviously we have this thing called size effects, and I'm going to go into exactly what that is. In fact, I'm going to go into it that hopefully you'll be able to describe it to your friends when you get back. When we talk about the copper and the barrier, we have this effective bulk resistivity of 2.2, but we have this mean free path to copper we need to consider, and this is where size effects come into play. One paper published by Interconnect Technologies kind of reset the roadmap here for the interconnect, where they tried to describe specific wire resistance according to the technology node using just IITC data with the bulk resistivity. And they showed that with this, with the size effects, there's this added increase in resistivity. So this was clearly a problem, and we needed to come up with a better solution to this, to describe physically what is going on. So clearly, as we're scaling down, we wanted to be able to understand and how to do predictions, and we need a model for that. We need something close for something fast, and describes physically what's going on. So I'm going to go into the background. I'm going to talk about line edge roughness, but I'm also going to describe in a little more detail scattering parameters, scattering effects, size effects that come into play. Then I'm going to go into the model derivation and talk about the model calibration with the experimental work. And then finally, we're going to see what projections can be made using looking at the IITC values that are targets that are currently out there right now for 2007, and I'll close. So when we talk about size effects, as we're scaling down, what we notice is increasing effective resistivity. So we add to the bulk grain boundary scattering and sidewall scattering, and I'll show that in more detail in the next slide. So adding on to that, we have increasing wire delay. So this is clearly a problem because you have talked about RC delay and overall impact on chip performance. And finally, one thing that's really special about size effects, well, the way I like to describe it is they are temperature independent. So what does that mean? Well, size effects are something where you have an obstacle. Say you throw a ball. There's going to be a wall there, or maybe not. That ball is going to hit the wall. No matter how cold it is outside, or no matter how hot it is outside, that physical barrier is going to be there. That is what size effects are. But temperature-wise, you can still decrease the overall resistivity. You just have this increasing trend. So when we look at the interconnect, we can no longer look at it this way, obviously. We have to look at it as a polycrystalline structure shown here, where we have first sidewall specularity. And sidewall specularity describes here where it is the percent of electrons elastically scattered at the surface. So what that means in plain English is when an electron approaches the surface, it decides whether or not it's going to preserve its drift velocity, and if it's going to continue onward, or if it's just going to stop at the edge. And so what we have here is, ideally, as a parameter, if all electrons encountering the sidewall here were to have a scattering parameter of 1, they would all they would lose no energy and continue down the conductor. The second parameter we look at is simply just grain boundary scattering, or reflectivity. And this is simply the percent of electrons reflected at the grain boundaries. And what this means is, obviously, when it comes to an interface in the polycrystalline structure for a grain boundary, it decides if this is going to be a reflecting plane or not. So it's going to decide whether or not to diffuse through the boundary, or if it's going to reflect back in. So ideally, we would like this value to be 0. We want 0 reflectivity. So if we had an R value of 1, what that would mean is that you would have total internal reflection. There's no escaping for the electron. So that's a basic summary there, and with a graphical representation. Now let's talk about the actual model that was founded by Infineon Technologies. They actually show that you can combine grain boundary reflectivity, shown here, with cycle specularity, and this is done using Matheson's rule, and with all the parameters shown here, and here we have alpha, which is defined as a function of the mean free path and the average grain size and the reflectivity parameter, and then AR is the aspect ratio, and that's defined, that's shown up here. But in industry, what we'd like to do is know, okay, well, what are the varying parameters of PNR? What have they found? And we can see that this turns out to be rather a process-dependent sort of thing. You cannot know exactly, you cannot say what for any particular company what it's going to be overall. So we have to understand this concept. Lastly, I want to go over what are the ideal parameters again. R is 0, P is 1, what happens? The effective resistivity is now equal to the bulk resistivity. So you can see here mathematically, this cancels out. If this is 1, this becomes 0. If this is 0, this actually just goes down to 1, and multiply that by the effective bulk resistivity becomes 1. So, equal to the effective resistivity. So that is something we've shown physically, and now we're showing mathematically how this equation works. So let's talk about line edge roughness. Again, when we look at line edge roughness, the first thing you kind of want to think about is how the lines are made, their pattern using photolithography. But we know it's an overall process. You know, as we've seen, we can control LER to some degree using certain tricks. We can understand how to change the material properties and so forth. But from the perspective of simply photolithography, if we talk about, say, an eye line, this was presented in this paper, you can have an effective line width of 40 nanometers, but the LER is about 15 nanometers. So this would mean that the widest part of the wire would be about 55 nanometers, where the thinnest part of the wire could be roughly 25 nanometers. But if we change the photolithography process, what we show is that we can actually have less line edge roughness. And here you have, yes, it is 60 nanometers as an effective line width, but the LER has not that much of a versus variation as shown here. So this is just one example, and this is where they were trying to come from as to how to describe LER and show it as a smooth variation going across. So what was initially done is that there was a numerical approach to estimate LER. And if you look at this graph here, you'll notice that we have the line described with LER on the sides, with W0 as the effective line width, which is simply the widest part of the wire minus the narrowest part of the wire. U is the amplitude of LER, and then we'll actually describe that as LER. U and LER will be used interchangeably in this talk. So if we talk about the widest part of the wire, it's simply W0 plus U, and if it's the narrowest part of the wire, it's W0 minus U, just like I was describing earlier. And lastly, we'll talk about the period of the wire. So to numerically estimate, go up or not.
Yeah, at some smaller scale, the
R1 for P that actually do work for.
and our next session.